Just a reminder, multiple is a number times some counting number. So, for example, we looked at multiples of 2. And so on. 2 is a multiple of itself, 2 times 1, right? Multiples of 3. There are some common multiples here. 6 is common. 12 would be common if I went one more step over there. So we can keep going. Multiples go on forever, right? So remember, we talked about it doesn't make sense to ever find a greatest common multiple because there is no such thing. Any pair of numbers is going to have a whole bunch of multiples. And sometimes it's nice to identify the lowest of those. Okay, so in this case, we could say the lowest of the common multiples here would be 6. Divisor is kind of the other end of the spectrum. If a multiple comes from multiplying, it's the after effect of multiplying. Divisor is what happened before or with division. So if we look at GCD, let's pick some more interesting numbers like 18. 18 has a bunch of divisors like 1, 18, 2, 9, 3, 6. And we have a routine by finding pairs of numbers that multiply together, and we can use that to find all possible divisors. We played with that earlier. Let's pick another number like, I don't know, 24. 1, 24, those are both divisors. 2, 12. What else do we have here? 3, 4. Oh shit, no. 8. 4 times 6. So do they have any common divisors? Sure. What do we have? 2 is common. 1 is common. 3 is common. 6 is common. Anything else? No. And here we're talking about the greatest common divisor. So we have divisors, we found the common ones. Of the common ones, 6 happens to be the greatest of the common divisors. So it's special. It's the greatest of these common divisors. Would it make sense to find the lowest common divisor? It would always be 1. Yeah, any numbers you look up, lowest common divisor is always going to be 1. It's kind of boring. Right. So it doesn't make sense to find a greatest common multiple. It doesn't make sense to find a lowest common divisor. But it does make sense to find a greatest common divisor or a lowest common multiple. We talked about some applications of that the other day. The biggest use of either of these is with respect to fractions. Greatest common divisor is very useful in reducing, getting a fraction to lowest form. Lowest common multiple is really nice when you're trying to add or subtract fractions or compare fractions to get a common denominator. So there are multiple methods for finding either the LCD or, sorry, the LCM or the GCD. And we went over a couple last class. We talked a little bit about finding divisors, then common ones, and then the greatest of the common, similar to this routine here. The book goes over another method I didn't go over in class. I'd highly recommend looking at that too. I'm going to review the prime factorization method, and then I'm going to go over the Euclidean algorithm for working with these things. So let's see. We made some cool, cute math discoveries the other day in terms of finding, let's go for the greatest common divisor first. And let's again pick on 18 and 24, partly because we already know the answer. So what I'd like you to do is get 18 and 24 into their prime factored form. What are the prime factors of 18? What are the prime factors of 24? So you could make a factor tree. Come on, pen. So my factor 3 there tells me that 18 is 2, and I like to write them with exponents. Similar, we can do the same thing with 24, and with 24 we should find it is 2 cubed times 3. Did anyone get that yet? Okay, I got some heads nodding, awesome. So let's see, I'm trying to find the greatest common divisor. So, well, let's see, both of these numbers are even, so they have a 2 in common, like this one right here. But 24 has too many 2's for 18's taste, agreed? 18 can only handle 1, 24's got 3. In common, they have at most 1. How about the 3's? They have at most 1 in common. Yeah, 24 has 1, it can't deal with 18's extra 1. Okay. So thinking about divisors, well, a divisor is a factor, isn't it? Yeah, so here are a whole bunch of factors. We looked for common ones. Well, we found 2 common ones, and when you put all the common ones together, in this case, the 2 and the 3, the GCD should be 2 times 3, or 6. Now, we found that with our listing method earlier. But it's once you break down what divisor is, what common means, and what greatest means, thinking about those, hey, welcome to class, nice hood. It's a good day for a hood. It's so damn cold, darn cold. Okay, so we put the idea of greatest common divisor. Let's look at this again with the idea of a lowest common multiple. So let's see, what color do I want? I can use red again, or black, red. So lowest common multiple. All right, so if I'm gonna build myself a multiple, that means like I have to take 18 and multiply it by something. And I could multiply it by 1 or 2 or 3 or anything. But the bottom line, 18 has to be in there to be a multiple of 18, agreed? So I'm just gonna start with 18. To be a multiple of 18, 18 says you better have a 2 times a 3 squared, because that's what I am. To be a multiple, I can then multiply that by anything I want, and I'm good. Let's look at 24's perspective. 24 wants a 2 cubed times a 3. Do I have enough 2's written down yet? Not yet. I need some more 2's. All right, so I'm going to multiply by how many more? 2 more 2's. And then, do I have enough 3's for 24? 24 is more than half, more than enough 3's. 24 doesn't care. So if I summarize that, then that would be what? 2 cubed times 3 squared. Okay, which is 8 times 9, or 72 multiplied out. And then we can test to see if that really is the lowest one by trying to remove any one factor. Like, what if I try to get rid of this 2 right here? Will any of the numbers freak out on me? Well, there's more 2's over here, so 18 would be okay. 24 would freak because I don't have enough numbers for it. It says, hey, that's not a multiple to me. Right? So I can't get rid of that. Can I get rid of any of the 3's? Who's going to freak out then? Then 18 freaks out, right? So I can't get rid of anything. So I must have the lowest one if I can't throw anything else out. I've got the minimum amount of stuff to either give me a multiple of 24 or a multiple of 18. Well, do I really have a multiple of 18? Well, let's see. Where's my highlighter? That's not it. That's it. Let's see, 18 is this stuff right here. Multiplied times anything is a multiple of 18. I'm good. Okay, how about 24? What does 24 want? 24 wants a 2 cubed times one of these threes. The other ones mean I have a multiple of 24. So can you see both 18 and 24 living in here? Okay, and again, when we're looking for a multiple, we're not looking for something that's a multiple at the same time. Is it a does 18 go into this number with no remainder? Yeah, 4 times. Does 24 go in there with no remainder? Yeah, I don't know how many times. 3 times? Yeah. Now, here's the remarkable thing though. Oops, new color. So when I found the GCD, I chose, say, this 2 and this 3 here. The LCM, however, picked a 2 cubed. There's the 2 cubed. And it picked the 3 squared, and the 3 squared happens to live there. So what can we say about the factors that the GCD and the LCD chose from what 18 and 24 had to give? Is there a possible pattern there? I can change the order, so there's not really cross multiplication, but there is something going on there. Whatever, yeah, once the GCD picks, whatever's left has to be the LCM, and it turns out it goes the other way around too. They picked the opposite amount of stuff in a way. So we'll test that on a different set of numbers to see that it's true. Well, what ends up happening is the LCM wants, it's a multiple, right? So I have to have basically all of the factors 18 has and all the factors 24 has, and I need the highest power of each. So the LCM is always going to choose the highest power of any prime factors. The GCD is going to select the lowest power of only the common factors, which are two opposite ways to choose stuff in terms of the factors. So I'm going to put up another set of numbers, and we'll just test that theory out again to see if they do choose the opposite set of stuff. Mm-hmm. For which one, LCM or the GCD? For the GCD. Mm-hmm. Yeah, you could end up with something like that, right? Yeah. So let's take, how about, let's get a little bigger. Let's try 420 and 60. I want 60. No, let's do, yeah, 60 is fine. All right, so I need you to do a factor tree on those and write down the prime factorization in power form, in exponential form. Uh-oh, I'm running out of room. Oops. Oh, darn you, stop that. Maybe you'll be able to join us live. I don't see her. Well, let's move you over here. And escape. Come on. Broken. There we go. Should look something like that. 420 is 2 squared times 3 times 5 times 7. Excuse me, 60 is 2 squared times 3 times 5. All right, so I'm going to move my factor tree out of the way. Let's go for the GCD first. So let's see, GCD needs stuff that's common to both. So let's see, we have a 2 squared that's common. We have a 3 that's common, and we have a 5 that's common. Okay. So GCD appears to be 2 squared times 3 times 5. LCM. So let's see, the way we built that one was, there's 2 ways to think about it. One is you pick a number to start with and see what you get. Well, I could start with 420. 420 is 2 squared times 3 times 5 times 7. And then I check to see if 60 needs anything extra. Does it? Nope. Okay, so the other way to think about it is the LCM chooses the highest power of all primes present. What's the highest power of 2 here? 2 to the second power. What's the highest power of 3? This one's available. Highest power of 5? That one's available. And highest power of 7? So there is the LCM looking at it that way. Did they get to choose 2 different sets of numbers contained in all the possible prime factors? Yes, just like before. Okay, so one thing that leads us to believe is that if we take, and you might want to try this out. Oh, this is kind of interesting. Because one number is a factor of the other number, some interesting stuff happens with the LCM and the GCD. What's the GCD here? 60. And what's the LCM? 420. Oops. Just because one number went into the other number. But because they choose opposite stuff, what seems to happen all the time, like this example right here, let me make a little space. Oh, shit. That's not what I meant to do. I've never hit that button before. Let's see, how do I zoom back? Maybe that one? Ah, there we go. Whew. I meant to grab that one, but my grabber is a little off. Let's move you there. And black, oh, come on. Having pen difficulties. Did I get black? Yeah. So if I take 18 times 24, that's going to be the same thing as taking 6 times 72. Because both 18 and 24 use these same factors just in a different order than 6 times 72. Right? 18 says take these guys, 24 says take those guys, multiply them all together. 6 says take the yellow ones, multiply by the circled red ones, same stuff. So double check if you have a calculator. What is 18 times 24? What is 6 times 72? So I'm going to use my Google calculator. 18 times 24, blow that up a little. Google says, off the screen, hide, 342. And if I take 6 times 72, I should get the same thing. 432, sorry, I read that totally wrong. Same number. So it turns out this is a rule we can apply in general. New screen. That if you have any 2 numbers, A times B, their product is always going to be the same as their GCD times their LCM. Because they use the same set of factors in different ways. Now the benefit of that for us, say you're way better at finding GCDs. Cool. then if you know the GCD, but this is unknown, you can just solve this equation for your unknown piece. So this tells me that the LCM of two numbers is always equal to the product, A times B, divided by the GCD. So if you're really good at finding GCDs, good, find it, divide that into the product of the original numbers, whatever's left has to be the LCM. Isn't that cool, Jared? Awesome. All right. So that's what we went over on, when was that, Wednesday? So next we're going to take a look at the Euclidean algorithm. And so, let's see, I think I'll keep picking on 18 and 24. So let's suppose we want to find the lowest common multiple of 18 and 24. We're going to use a new routine. So like with 60 and 420, 60 happened to go into 420. And if you notice that one number is a multiple or a factor of the other, then you have the GCD and LCM right there in front of you already. You don't have to do any work. And it turns out you can use that as kind of another way to go. So I could check, does 18 go into 24? Well, let's see, 18, let's see, it goes in there once, right? 1 times 18 is 18. I do my subtraction and I get what, 6 left over? So let's see, what did I found? I found that 24 is equal to 1 times 18 plus 6. There's a remainder, right? So it didn't work. But turns out I can take this a step farther. Next thing I do is I take 6 into 18. So I'm going to do that up here. Let's take 6 into 18. Let's see, 6 goes into 18. How many times? So, oh my gosh, 3 times. 3 times 6 is 18. Remainder is 0. So 18 is equal to 3 times 6 with a remainder of 0. So it turns out if you repeat this process with your remainder and the previous divisor, once you get a 0 remainder, this number right here has to be your GCD. Okay, so I said I was going to find the LCM. How can I use the GCD to find the LCM? Yeah. Say that one more time. No, let's go the other way. We want to multiply our two numbers, 18 times 24, and then we want to divide by the GCD. And that'll lead me to the LCM. But this division technique that leads to divisors is what's called the Euclidean algorithm. So we'll repeat that on a bigger set of numbers. Sometimes it happens fast in a few steps. Sometimes it takes a long time. There is no perfect method. Sometimes one works better than the other. It just depends on the numbers involved. So let's see, I'll pick a couple numbers that might have been something in the homework. Oh, those are some big problems. Let's take, oof, do we really want to do that big? I don't know if I want to do that big. Let's do a little smaller first. How about 220 and 2,924. So here's where a calculator might be nice to help with the division. We need to know how many times 220 goes into 2,924. No, we just want to divide. So we're going to use the Euclidean algorithm. So using the Euclidean algorithm, we want to say, okay, the 2,924 equals what times 220 with what remainder? So we want to find what's called the quotient and the remainder here. So we whip out our handy dandy calculators, 2924, oops, 24 divided by 220. And I get 13 with a little bit left over. And we got to figure out how much is left over. Well, we just take 13 times 220 away from 2924, we'll have that. What is it? You got a remainder of 64. Anybody else get that? Okay. What's that? Oh, you wrote the numbers wrong? Okay. So 64 is our remainder. Okay, so the 13 is what you call the quotient. The 64 is what we call the remainder from the division. And we can just try again. So next we take 64 into 220. So we're going to rewrite 220 as some number of 64s with a remainder. Goes in 3 times. Or is 3 too many? No, it should go in 3 times. 182, okay. 192. So then we have 28 left over. So we got to do a little division, subtraction. What are we going to do next for division? $28 into 64, yeah. So it's always going to be, highlighter, the remainder into the previous divisor, remainder into the previous divisor. And you keep running that until you get no more remainder. So then we want to figure out 64 is how many 28s plus what remainder. So it goes in there, what, 2 times? That's 56 with 8 left over. And we got to keep going until we're done. So let's see, 28 divided by 8. With what left over? 4 left over. And then now we should see the n coming in. 8 is equal to 2 times 4 with no remainder, oops, plus. So no, so what we figured out is the last remainder before the 0 is our greatest common divisor. So that means 4 has to be the greatest common divisor. So that should be the GCD. So one question is, why does this work? And it has to do with the rules we talked about back in section 1 of chapter 4. 4 goes into 8, right? So shouldn't 4 go into anything times 8? Okay, so I'm just going to check off some stuff here. So we know 4 goes into 4, and 4 goes into anything times 8. Well, okay, 4 goes into 8, and let's see. Oh, so 4 goes into all this stuff, so that means it goes into 28. Okay, so 4 goes into 8 and anything times 28. So that means 4 goes into all of this stuff here. And we just keep following that up. 4 must go into 64 then, right? Because 64 is that stuff. Okay, we already know 4 goes into 28. So that means 4 must go into this guy, and 4 must go into anything times 64. So 4 must go into 220. Go up one more time. 4 goes into 64, 4 goes into 220, so it goes into anything times 220. So 4 must go into 2,924. Okay, so it's kind of a way of using that rule. If we know 2 numbers are a multiple of another number, then the original number must go in. And so we just follow that train of logic back up. Sometimes this is easier than doing a bunch of factor trees and picking out the factors. Sometimes the factors are easier. So it's just another method. If you like this method and it works for you, then you can always divide 4 into the product of these guys, and there's your LCM. And that's the Euclidean algorithm. And sometimes it's more efficient on bigger numbers than factoring into primes. Because factoring into primes is generally quite a bit of work. This is called the Euclidean algorithm. All right, so I'm gonna have you try it on a pair of numbers. Ooh, geez. Let's pick one out of the homework. The book gives an awfully big one here. Oh, what the hell, let's try it. You're definitely gonna want your calculator ready for this one. This is problem number 3 in the book. The numbers are 14,595 and 10,856. And so we're going to use the Euclidean algorithm on that. So you're going to do some division and find remainders. And the remainders are key to making that happen. So whip out a calculator, see what you can get done. Turns out it doesn't matter the order, because if you do it in the wrong order, it throws the other number back at you as the remainder and makes you do it again. It doesn't matter what order you pick, it'll straighten itself out. The method will. So for example, if usually we take the smallest number into the biggest number, but if you tried to go the other way, if I tried to take 14,595 into 10,000, what I'd find is that 10,856 is equal to no 14,895s plus a remainder of 10,856, which forces me to do it the other way. So the algorithm automatically flips itself around if you pick the wrong order to start with. Yep. Yep. So yeah, it's only going to go in there once, and the remainder is whatever the difference is of those two. So the first step ends up looking like that third line there. That was one of the starting numbers. These are the two numbers we're trying to find the GCD for. I can use my calculator. Where? Oh, what do you mean you got one left over at the very end? Uh-huh. Okay. You keep going. You're not done. Let's see, I gotta get my remainder here. What'd you get? Really, what'd you get? Did you really? What was the last remainder before the 0? So what happened after this step here? So then, yeah, plus, okay, then we take 361 into 3378. 9 times 361 plus 129. Okay, so 129 goes into 361. Plus 103. And let's see, 129 equals 1 times 103 plus 26. 26, oops, shit, 103 equals how many 26s? Remainder 25, okay. And then 26 is 125 with a remainder of 1. And then 25 is equal to how many ones? 25 ones plus a remainder of 0. So that has to be the GCD. The previous remainder from the 0 has to be the GCD. Okay, so I did this problem a different way just to see if that was right. So let me just show you this, and I'll back up for you a second, Morgan. So I did a factor tree on 14595 and found, and this was quite a bit of work, 2 times 5 times 7 times 139. And guess how many times I had to check numbers to get that 139 to work? Quite a few, okay. And then I found that the 10, 8, 56, did I get that right? Yeah, was equal to 2 times 23 times 59, and that took an awful lot of work too to get that one right there, because there's a big gap between 2 and 23, right, where I'm testing stuff. There's a big gap between 23 and 59 where I'm testing stuff. So the question is, what is more work, doing a factor tree and looking at, and what, oh yeah, but let's see, did I do that right? Oh, this should be a 3, sorry, not a 2, that's a 3. What primes do they have in common? None. None. They don't have any common primes, so the GCD has to be 1. which the Euclidean algorithm told us also. So the question is, what is computationally easier, factoring and coming up with those as the prime factors, or doing a bunch of divisions with remainders? I don't know. In this case, it seems like it might be a trade-off. If you're bored later tonight, try doing a factor tree on those numbers. It's quite exciting. What's that? Yeah, so once you get used to the system, it flows kind of nice. If you have a calculator with a remainder button, it's even better. Some calculators have remainder buttons. You just click, because all you really need is the remainder. You could care less what this number is, as long as you have the right remainder. Am I going to, or do they exist? So I don't know. That's a good question. Are there more? So when two numbers have one as a greatest common divisor or factor, they're called relatively prime. So are there more pairs of numbers that are relatively prime than not? I have no idea what the answer to that question is. Have I ever even thought of it before? I think I have. Yeah, sometimes two numbers have no greatest common divisor. Sometimes the Euclidean algorithm works really fast in like 3 or 4 steps. Sometimes it takes like 10 steps. Sometimes finding the prime factors isn't too bad. Sometimes it's a nightmare. No matter what, it's hard. And when I teach pre-algebra, I remind people that we're just doing whole number stuff, but people get PhDs studying this shit. And it actually turns out to be very important stuff to computers, and we all like computers because today is Cyber Monday, damn it. And we should be all on our computers buying stuff. Anyway, wow. Okay, I won't put that problem on the test. It'll be a little bit easier. But I do need to know a couple of different algorithms for finding GCDs and LCMs, whether it's the prime factorization method or the list method or Euclidean algorithm, or dividing the product of two numbers by their GCD or LCM. We got a bunch of tools at our disposal. I highly, 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 highly recommend you look at some of the stuff in the books. They show some really cute pictures about this. And you paid a lot of money for that book. And I think it's good. I wouldn't have picked it if it was a crappy book. Please read it. Okay, that's about it in chapter 4. This division algorithm, the Euclidean algorithm, it's exhausting sometimes. Well, you know, that happens when you're doing a factor tree too. I mean, we're always going to make problems like that. So it's nice to have multiple ways to look at it. Like, I mean, I was looking at that one, like, holy shit, did I screw up? Right. So so I mean, how do you know? I mean, most of the time we're playing with numbers we're already familiar with, but the kids are going to be 18 times 24 is going to be a hell of a problem for a 4th or 5th grader, a 6th grader. Just like 14,595 and 10,856 is a hell of a problem for us. Right? It's unknown, right? So having different methods is important sometimes, but you will get 2 complaints from students and parents. You know what the 2 complaints were? The teacher showed me one way, I don't get it, right? So my teacher sucks. Or the teacher showed me too many ways and confused me. You cannot win that battle, but you got to keep trying. Is there a best method for most people? Maybe. Let somebody else do it. Yeah, there's 2 kinds of people in the world. People who can do math and the people they take care of. We don't want anyone to have to take care of us. We want to be able to do it ourselves. All right, so I think we've exhausted that. We're going to play with some toys. I'm going to stop this recording and start a new one. How do I do that? Over here somewhere. There it is. Stop and stow. Hi, Debbie.
Hello.
Surprise. Oh, shit. Can you still see me and hear me? Oh, you're over
I
here. Sorry, this is confusing. I have the screen in a different spot. That's better. So I am going to stop this recording, but I'm going to start a new one in 5 minutes. We're going to take a look at activity 1 in chapter 5. Okay?
Okay.
All right.
Sounds
I'll
good.
see you in a minute.